All right, so let's begin our class number 22. We're continuing our discussion for multiple regression model when we have qualitative regressors. On the right-hand side, we have dummy variables, or we have categorical variables. So last time we looked into a bunch of examples from the textbook, and for example, we looked at what is the effect of owning a computer on college GPA score, and some other examples. Then we were discussing about this one that we were looking at the wage versus education, experience, tenure, and gender. So specifically, we use a dummy variable female in the model. And we said that, okay, it seems that in this model, on average, females are earning 20.7% less than male, holding everything else constant. Then we discussed the idea that what if you want to add a new dummy variable in the model? So, and that new dummy variable is marriage, right? So what if you're interested to see what is the interaction between gender and the marital status as well? Because yes, in this model it says that females are earning 29.7% less than male, but what if I want to see what is the difference between married female and single female? And married male, single male. And basically I want to compare these four groups, right? So for that, we said there are two general ways to do that. So the first one is what we call using multiple categories. The second one is what we call using interaction terms. So last class, at the very end of the class, we discussed about this using multiple categories. Basically, the idea is that make sure that you make multiple categories out of your dummy variables. So here I have two dummy variables, female and marital status. So 2 multiplied by 2, I can get 4 different classes. So married male, married female, single female. And of course I have to drop one of them from the model. The one that it is dropped, we call its base group or benchmark group. So quickly, for example, we said, so this equation suggests that married male is earning 21.3% more than the group which is missing from the model, right? So our base group, which is single men, right? Then we talked about, we answered these different questions, but now in this class, we want to explore the idea that, okay, what is the second approach? So again, there are two approaches. The first one using multiple categories, the second one using interaction terms. So obviously we're going to use this interaction terms as female multiplied education in the model. And now let's continue our discussion and see what is that other neat version of doing these things. And that neat version is using the interaction term. So I can say, so here we're going to start with the interaction term between female and education, and later on we are going to go back to that example of gender versus marriage by adding interaction between gender and marriage, female and marriage. But let's start with an example which is easier to follow, and then we get to that more complicated one. So I'm going to introduce you to something called interaction terms with dummy variables. What's the motivation? Do you remember from the very beginning? So, and again, guys, I know that it's becoming a lengthy video, but the next class is going to be a very short one. Okay, we saw something like this. If I have only female, if this is the model, if I have only female and education in the model, we said that maybe this is a line for female, this is a line for male. We already said that we don't like this one because it's saying that for any level of education, on average, female are getting less than male. So what if we want to have something like this? Okay. If I want to, so here, we only allow for shift in intercept. So we call it intercept shift. We want to work with a model that we have shift both in intercept and slope. So that's the idea. Whenever you want to do something like this, you have to add the interaction term. So this interaction term is going to do this job for you very beautifully. Now let's look at the mathematics behind it. It's very easy to follow, so don't worry. So let's say we are regressing log wage on female education, and that this interaction term. And now let's see, what do we have? Again, remember, your female can be either 1 or 0, right? If female is 0, what is the intercept? So this is, look at that, this is 0, female is 0, the intercept is going to be beta 0. If female is 1, what is the intercept? The intercept is going to be beta 0 plus delta 0. Okay, this is the intercept. Now, if female is 1, what is the slope? So be careful of this slope. And whenever we say a slope, we're interested in the marginal effect of education on wage. So if female is equal to 0, so the slope is going to be beta 1 plus delta 1 multiplied 0, so it's beta 1. If female is equal to 1, so the slope is going to be beta 1 plus delta 1 multiply education, so I have beta 1 plus delta 1. So we have a shift both in intercept and the slope. So this is exactly what we wanted to get, right? So let me show you a visualization. I'll come back to this. This is what we wanted, and this is what we get. So here we can have change both in intercept and in slope. The slopes are different. And we can have different combinations, right? So on the left, it's an example that delta 0 is negative and delta 1 is also negative. So it says that females are going to start from if the education is 0, they're going to start from a lower salary, and if the education increase, look at that, delta 1 is less than 0, so their slope is less than the slope for male. Or we can say, okay, females start from a smaller number, but their slope is higher than the slope for male. So at some point, they are going to say that, okay, I don't know what is that point in the data, but let's say it's PhD. Maybe females with PhD are going to earn more than males with PhD. But I don't think that's something that the data support. So my understanding is that for data today, as of 2020, we have something like this. And maybe the maximum level of education is here. So let's say, yes, females are going to start with lower salaries, but the distance is going to get smaller and smaller. But unfortunately, even at high educated levels, even though the difference is small, but it is still there. Okay. Again, it's upon our generation to fix this going forward. All right, now let's go back to the previous slide. So with this, we can ask many interesting hypothesis questions, right? So let's say the first question that I can ask, again, you are the researcher, you are the owner of your research, you can ask whatever question you have. So one interesting hypothesis question is, if delta 1 is equal to 0, what is delta 1? It's this one. If delta 1 is equal to 0, basically you're asking if the return to education is the same for both male and female. Again, return to education is the same for both male and female. So you're testing if there's only a shift in intercept. This is what you're testing. You're testing if the slope for them, both of them are the same, which is beta 1. Or you can ask another interesting question. You want to say if the gender matters at all or not. Because look at the dummy roles. I have female, delta 0, and I have female here, delta 1. If I want to test if delta 0 and delta 1 collectively are equal to 0, I'm testing if both there is no change in intercept, no change in slope, so male and female. I want to test that if this is the case, and I hope that that's the case, right? So this is one question. This is another question, and yeah, you can ask if the slope alone is going to change or not. So again, you can ask many different hypothesis questions, but these are the most common ones. First of all, if return to education is the same for both male and female. And secondly, if gender matters or not at all. Okay. Now, so we already talked about these things. We calculated the slope and the coefficients and the intercept as well. All right. Now, with this new knowledge, let's go back to our well, let's put some numbers into it and then we'll go back to that. So this is the last, I think this is the last example that I'm going to go over interpretation, but the rest of them are straightforward. So let's interpret a bunch of these red rectangles that I highlighted. So we're regression log wage on female education. Now I'm adding female multiply education experience and experience squared. Okay. So your task number 1, what I want you to always do is to take derivative, take derivative, take derivative. So if I ask what is this number, so you have to take derivative with respect to female. So log derivative of wage with respect to female. So what do I have? Minus 0.227. Where else do I have female? Here. So minus 0.0056 multiply education. Do I have female anywhere else? No. Now I can interpret that. So how do I interpret this number? This says that females on average will earn 22.7% less than male, holding everything else constant, and education is equal to 0. Because if education is not equal to 0, this number is not minus 22.7%, right? So again, take derivative. So that's one thing. So let's do this one. Does this mean that there is no significant evidence of lower pay for women at the same level of education, experience, and tenure? Hint, find the partial effect of being female on log rate. So this is what we did. The answer is no. That's only the case if education is exactly equal to 0, right? That's the case if the education is 0. And then to answer the question, one has to recenter the interaction term, for example, around education 12.5. Well, this is something that you guys are going to do in homework 9, so I just leave it as an exercise for you. But again, there is a step-by-step guidance in homework. I think it's homework 8 for you guys. This is homework 8 for you guys. I should have updated this slide. But anyways, you will see the homework for chapter 7. And it will walk you through the interpretation of that. So this is one thing. Another thing, now how can I interpret this one? Estimated return to education for men, base group. What is the estimated return to education for women? So we are going to say return to education. So let's take derivative with respect to education. Again, log wage to education. If I take derivative with respect to education, then what do I have? Sorry, let me erase all these things that I don't want to use further. Whenever you see education, it shows up in the derivatives, right? So 0.082. Where else do I have education? Here. So the derivative is going to minus 0.0056 female. Okay, make sure that you take derivative correctly. Do I have education anywhere else? No. Okay. Now, how can I interpret this number? So let's say that 8.2%, let's do 8.2% because I can plug female is equal to 0 and 1 and get two different numbers, right? Starting from female equal to 0. So this means that on average, the males, the partial effect of education on wage for male, again, for male is 8.2%. So this is the statement that we have. This is the estimated return to education for male, 8.2%. Question is asking, what is the estimated return to education for female? It's going to be 8.2% minus 0.56%. Okay, so this is the answer to this question. And then finally, what do we have here? No evidence against hypothesis that return to education is the same for both male and female. Find the partial effect on education level. Okay, so here, how do I say something like this? Because I'm calculating the t-stat. The t-stat is 0.0056 divided by 0.1. It's less than 1, so it's not significant. So this is equivalent to asking a question like this. Like this. Delta 1 is equal to 0. Okay. Look at that. Delta 1 is the coefficient of female versus education. Female versus interaction with education. This is my delta 1. Delta 1 is significant. So it seems that the partial effect of education on wage is independent of gender. Or at least we fail to reject that it is irrelevant. All right. Now, what else? Let's look at yet another example. We are regressing cumulative GPA on female, and SAT score. So the interaction between female and everything that I have in the model. So what do I have in the model? So let me back out. Let's look at the coefficients of beta. So I have SAT, I have high school percentage, I have total hours. So this is total hours of college courses. And I have, that's it, right? So these are the three variables that I have. Now I want to add a new variable called gender, and I will add gender and all the interaction of gender with my variable. So gender and SAT, gender and high school percentage, gender and total hours, right? So I can give them proper name, delta 0, delta 1, delta 2, delta 3 versus betas, right? Now let's ask some interesting hypothesis question. So the interesting hypothesis question is that, does gender matter at all? Okay, so if I want to ask, does gender matter at all? So I need to make sure that delta 0, wherever I see gender, I want to see that those coefficients are equal to 0 collectively or not. This is a very interesting hypothesis question, right? If I want to answer a question like this, remember, this is a nested model. For nested model, we can use F statistic. F statistic has something to do with unrestricted versus restricted model, right? So this is an unrestricted model. This is a restricted model. Going back to R, so we can simply do it in R, construct the unrestricted model and use that linear hypothesis function from R and then be done. So let's do that very quickly. I'm going to do it in this slide, but let's do the regression and put some numbers into it. So I'm going to throw data at these unrestricted and restricted model and look at the numbers. So these are the numbers, okay? And remember, we only need to do the regression for unrestricted and then use the linear hypothesis function and pass the unrestricted model to linear hypothesis function. Okay, so these are the numbers. So it seems that female itself, we're going to look at the beautiful output in R, but we can quickly eyeball the significance. This is not significant. Look at that. This is not significant. This is not significant, less than 2. Obviously not significant, obviously not significant. So it seems to me that these coefficients that has something to do with gender, they are not individually significant. Be careful. They are not individually significant, because what I just did, I was calculating the t-stats for any of them. So 353 divided by 411, less than 2, not significant. This one, not significant, and etc. So remember, t-stat is used for individual tests. They are not individually significant. So that's one thing. Now, what was my hypothesis? The hypothesis was that if they're jointly significant or not. So I haven't answered that question yet. What I have already answered is that if they're individually significant, the answer is no. So test individually, the hypothesis that the interaction effects are 0 cannot be rejected, right? So they are individually not relevant. But why we cannot conclude that cumulative GPA, well, this is another thing. Why we cannot conclude that cumulative GPA is this number less for women than men. So go back to cumulative GPA. It's asking you why we cannot say that on average females are getting 0.353 points in terms of cumulative GPA less than male. So that's a question. Because, as always, you have to take derivative with respect to female here. So what do I have? Minus 353. Where else do I see female? Here, plus 0.0075. There are 3 zeros. SAT. What else? Minus, I'm here, 0.00055 high school percentage. What else? Minus 0.00012 total hours. Okay. So the answer to this question is that yes, females on average will get this number less than male only if SAT, high school percentage, total hours is equal to 0. Does that make sense? No, because zeros are not meaningful numbers. So I have to put the averages and then say something about the average partial effect. All right, so we answered this one as well. Now, let's go back to our joint significance. Let's go back to our interesting hypothesis test using R. So in R, it's very simple. Again, whatever we are doing in regression analysis, application in R cannot be easier at this stage. I get it. You know, if I want you to do these things at the beginning of the semester, it's overwhelming. But as of now, you are super familiar with doing things in R. So at this stage, it shouldn't be that difficult. So let's look at this model And by the way, guys, you have the code for all these things in our script. So maybe next class, when I have some time, I will review these cases very quickly. Let's say I ask two interesting hypothesis questions. Case number one, case number two. In case number one, I want to see if both the intercept difference and the slope difference are zero. Literally, I want to see that if the line of male and female overlap. So I want to say if there is no change in intercept and no change in any other slopes. So delta 1, delta 2, delta 3, I don't know, whatever, wherever it shows up in the model. If it is 5 of them, all the 5. So I'm testing if all of them are zero collectively. So this is case number one. Okay, so let's do that. So we are going to pass this model and then call, this is the unrestricted model. And then what do I have here? This is the delta 0 female. This is my delta 1 female interaction SAT. Be careful, you have to put column. Female interaction SAT, female interaction high school percentage, female interaction total hours. So it really doesn't matter if you put equal to 0 or not, because in R, by default, it's going to be equal to 0. Then what's the answer? And let me just rewrite this thing. We're testing male and female overlap. What's the answer? Look at that. P-value is super small, nice. So, well, again, nice is relative here. So we reject the idea. I should back out nice. Again, nice is, it's not a good word, because we reject the idea that this is the case, which is that. Okay. So this is question number one. Question number two, case number two, we want to see if only the slope differences are equal to 0 or not, right? So we want to see, we agree that the intercept is going to be different. We agree that the intercept is going to be different, but we want to see if the slope is exactly equal to each other. So basically, I'm testing if delta 1 is equal to delta 2 is equal to delta 3 is equal to 0. Again, we agree that there is a change in intercept, and we want to test if there's a change in, if there's a shift in the slope as well. So this is the setup, so we can easily do it in R. And then now let's look at the output. Okay, now if the p-value is large, so we fail to reject. Maybe I can say now I'm happy. So it seems to me that, well, here at the top I was unhappy. No, we cannot say that gender does not matter at all. Okay, but at least if I agree that, okay, there's a shift in intercept, but it seems to me that we fail to reject that this is the case. So maybe this slope is not different than 0. So this is a good idea. Okay. Now we can look at these numbers in R as well. So let me see if I have it here. Yeah, actually we do have it. So it's fun. Actually, this is a very fun experience. So model number one, this is our unrestricted model. We have everything. We have everything in the model. Model number two is a restricted model, right? And again, unrestricted versus restricted, we are using Stargazer output. Now, what are these restrictions? We are only restricting the slope variables. I'm not restricting the delta 0 itself, because the delta 0, this is the interesting research question. I don't want to get rid of it, okay? But the fun part is, look at that. Remember, let me remind you of the setup of the question. We're regressing college GPA, and we want to see if it had something to do with gender. If I look at the unrestricted model, it seems that females on average are getting less than male, because this is a negative number if SAT high school percentage and total hours is equal to 0. Okay, but again, it seems that they're getting less grade than males, right? There are a couple of things going on. First of all, this number is not significant, so you should not super interpret that one, okay? But the sign is negative, so maybe you think that girls are getting less grade than boys, right? But if I get rid of all the interactions, but have the female in the model, then look at that. This thing turns out to be from negative to positive, and now it's significant. So this is the interesting part. So I can interpret this, but I cannot interpret this because it's not significant, right? I can say, yes, girls are gaining 0.31 points higher than boys in terms of college GPA, and it is significant, and data is supporting that. And look at the adjusted R-score, 39, 39. So there's no big difference between adjusted R-score. So which model should I go with? Absolutely model number 2. Why? Because one of the most interesting research questions that I had, which was the effect of gender on college GPA, turned out to be significant in one model and not significant in the other one. Okay, so the idea is that maybe I should not have overkilled the model by adding all the interaction between gender and all explanatory variables. Maybe having that gender alone in the model was enough, and that's the answer. Okay, now it's time to go back to our setup. So this is one of the questions from homework as well. Do you remember you were interested to having both gender and marriage in the model? Okay. We said that there are 2 ways to do that, and I call it using multiple categories versus interaction term. The first way is to say that look at different combination of the 2, married male, married female, single male, single female, and pick 3 of them, again, K minus 1 of them as dummies and leave the other one as base group. So this is one way that we already did. Okay, how we can do it in R? So the variables that I have in the model is female and marriage. So if I want to construct married male, so do I have married? Yes, I have. But male, do I have male? No. So I have to construct male synthetically. So what is male? 1 minus female. So for married female, do I have married? Yes. So what is female? Yes. Single female, do I have single? No, I have to do 1 minus married. Multiply, do I have male? No, I have to do 1 minus female. Okay, so this is how we construct these 3 variables in R, basically here. And make sure that you have to use this I function, okay? Because otherwise R doesn't understand. So first one, married male. Married, do I have male? No, I use 1 minus female. And please do stars, because R doesn't understand if you just say multiply. So you have to say star. Star stands for multiply, right? So married male, married female, single female, right? Single is 1 minus married, and make sure you use this I. And the rest of it is, piece of cake. Plug wage on these 3 variables, and education experience squared, tenure squared. So you have done the rest. We're using wage 1 data set. This is one way. The other way, now that we know what is interaction, we can use, we say, you know what? I use female, I use male as 2 separate dummy variables and the interaction between the 2. Okay, so I can show it to you that this case is going to cover all these married male, married female, single female. Okay, and that's easy, right? So if F is equal, so let's say we want to get this one, single female. So if female is equal to 1, married is equal to 0, I will automatically get single female, right? So if I plug these numbers here, I will get single female. Okay, so female is equal to 1, married is equal to 0, so this is going to be 0 as well. So now let's run, and again, having this one in R, this is also easy. So I have female plus married and plus married column female, so this is the interaction term. Let's look at the output. So this is the last slide. Let's look at the output of these 2 regression, and I have a couple of final thoughts on these 2. So when should you use model number 1? When should you use model number 2? Model number 1 is the one that I say we're going to use different multiple categories, right? Married male, married female, and single female. Model number 2 is the one that I say we're using interaction term. Okay. First thing that I want you to notice that in terms of the coefficient for the rest of the variables that has nothing to do with either gender or marriage, nothing changes. Look at that. This number is exactly equal to this one. In terms of the constant, again, exactly the same. In terms of the goodness of fit of the model, must be the same. Look at the R square, adjusted R square. They are exactly the same, and they must be the same. You should not be surprised, okay? So what's the difference between the 2 models? The difference between the 2 models is only for the interpretation. I'm going to tell you that you use model number 1, these different classes. This is a better setup if you are interested in testing for wage differential between specific groups. So you want to say that I'm interested to see what is the difference between wage of married female and single male. If you want to answer a question like this, you better set up it like this, model number one. Okay. However, if you want to answer a question like, does the gender matter at all? Does the marriage matter at all? If you want to answer questions like intercept shift or slope shift, intercept significance, slope significance, then obviously you have to use the interaction terms, right? So model number two allows to easily test the null hypothesis that the general gender differential does depend on the marital status or not.